In this video, we'll discuss the relationship between the linear chain conditional random field with the hidden Markov model. So we've in the previous video talked about whether there were alternatives to the linear chain conditional random field for sequential classification, discriminative alternatives that might be more appropriate when we have a lot of training data. This has led us to talk about the maximum entropy Markov model, and I've mentioned why it suffered from a problem known as the label bias problem, where observation further away in the sequence would actually not have any impact on the prediction and the marginal probability for the label at positions early in the sequence. So another alternative to the MEMM, which is well known and we've actually mentioned in passing in previous videos, is the hidden Markov model. So in the hidden Markov model, instead of assuming a generative story where we are given some inputs and then those inputs in the sequence have then generated the labels, we have an inverted generative story where the labels have first been produced, and then from the labels the sequence of observations have actually been produced from this. So instead of producing the inputs and then the labels, it's the other way around. And actually in HMMs, we usually define something known as the emission distribution, which tells us how the inputs were generated from the label, so P of x given y. So from this, we actually get a full joint distribution over both y and x, both the sequence of labels and the sequence of inputs. And if we have a joint probability from this, then we can just compute P of y given x by just dividing by the marginal probability of x, which means that we can have an expression for minus the log the conditional probability of y given x, and we could try to optimize that, and so essentially optimize our model to assign high conditional probability on the labels given the inputs. So discriminative training of HMMs is actually used a lot in speech recognition. It's known as maximum mutual information training. And we can show that we don't have the same label bias problem anymore. So that's an advantage. However, the directed nature of the HMM can make it a bit more complicated to train. So the optimization problem associated with training can become a bit more complicated, because if we write down the HMM as a factor model where it's a product of factors, as we've discussed before, the factors now need to be normalized probabilities. And so this has certain consequences in the optimization of the model. And it can also be somewhat difficult to define a good distribution over the sequence of inputs x. If the vectors x1, x2, and so on are real valued vectors, defining distribution over real valued vectors is actually not a trivial thing to do. Whereas in CRFs, because they're conditional, we totally sidestep this problem, and yet we don't actually suffer from the label bias problem, much like in the discriminative HMM. So one can think of a conditional random field, or linear chain conditional random field, as the sort of best of both worlds solution between a discriminative hidden Markov model and a maximum entropy Markov model. So, to sum up, while the maximum entropy Markov model can be perhaps easier to train than a hidden Markov model, it suffers from the label bias problem. And the hidden Markov model, if we were to train it discriminatively, though it's possible and people do it in speech recognition, it can be harder than the linear chain conditional random field.